Students, welcome to my continuing lecture on Special Topics number 1, a systematic review of chapters 1 through 3, and then now chapters 4 through 5 from the last semester of General Chemistry. Okay, so I realize that you guys who are in my second semester General Chemistry class have already taken and learned all of these things before, so this review might in some parts feel insulting to your intelligence, but in other parts I hope that it will be a welcome refresher of things that you may have forgotten or maybe a little bit hazy on. Anyway, in today's exciting review we're going to do some cool stuff from chapters 4 and 5, but first I want to share with you one of my personal favorite chemistry cats of the day from quickmeme.com. This one says, Le Catelier. Yeah, I love that. Now, if you didn't get that joke, well, you need to learn chemistry. Okay, I also wanted to share you something about some illicit drugs, because I occasionally have students ask about them because I'm a chemist, and they all assume that I'm really big into illegal drugs, which I'm not, just so you know. But this one is interesting. So, according to Wikipedia, it says ephedra usually refers to the plant Ephedra sinica. E. sinica, known as Chinese ma huang, has been used in traditional Chinese medicine for 5,000 years for the treatment of asthma and hay fever, as well as for the common cold. Several additional species belonging to the genus Ephedra have traditionally been used for a variety of medicinal purposes and are possible candidates for the soma plant of Indo-Iranian religions. Native Americans and Mormon pioneers drank a tea brewed from other Ephedra species called Mormon tea or Indian tea. In recent years, the safety of ephedra-containing dietary supplements has been questioned by the medical community as a result of report of serious side effects and ephedra-related deaths. In response to accumulating evidence of adverse effects and deaths related to ephedra, the U.S. FDA banned the sale of ephedra-containing supplements on April 12, 2004. So this is a while ago, but I actually remember when this happened. A lawsuit challenging the FDA ban was upheld by a federal district court judge in Utah on April 14th of 2005. The FDA appealed this ruling, and on August 17th, 2006, the U.S. Court of Appeals for the 10th Circuit upheld the FDA's ban of ephedra. One of the main targets actually went by the trade name of fen-phan, in case you guys might remember that. The sale of ephedra-containing dietary supplements is currently illegal in the U.S. because of high risk of ephedra-related adverse events. The stimulant and thermogenic effects of Ephedra sinica and other ephedra species are due to the presence of the alkaloid ephedrine, shown right here, and pseudoephedrine, both natural nervous state effectors. These compounds stimulate the brain, increase heart rate, constrict blood vessels, which increases blood pressure, and expand bronchial tubes, making breathing easier. Their thermogenic properties cause an increase in metabolism, evidenced by an increase in body heat. Looking at these two structures, you might notice that they have some stereochemistry right here. This stereocenter right here in the three-dimensional configuration around it is exactly the same between both isomers. You'll notice that I've got a dash bond to this nitrogen and a dash bond to this one. But the stereochemistry at the opposite stereocenter is dashed to this OH and wedged to this OH. So they're not enantiomers. They're not exact opposites. Neither are they exactly the same. They're halfway in between, so they're kind of half enantiomers. There actually is a technical term for that I won't teach you in this class, but I will if you go on to take organic chemistry from me. So thank you for indulging me with letting me go down this memory lane here. Well, I shouldn't say memory lane, I mean interesting lane with the coverage of illegal drugs. Alright, so after today's presentation that will review chapters 4 through 5, you guys should be able to use Avogadro's number to interconvert between moles and numbers of atoms, memorize the solubility rules from table 4.1 and use them to classify different compounds as being soluble or insoluble in water, identify the precipitates that form in precipitation reactions, write a net ionic equation, calculate an aqueous solution's molarity and concentration, use molarity to calculate grams of solute, write net ionic equations for neutralization reactions, and perform specific heat calculations. It's a long lineup. Let's go ahead and get started, beginning with Avogadro's number. What in the world is a mole? We chemists often use this thing called a mole to measure stuff. What is a mole? Well, strictly defined, a mole, also called Avogadro's number, is 6.022 times 10 to the 23rd. It's kind of like a dozen, except instead of being 12, it's 6.022 times 10 to the 23rd, which, by the way, is a huge number. So why in the world do we care about such a bizarre number? Well, as it turns out, a mole happens to be the exact number of atoms present in a sample that weighs that sample's atomic or molecular weight. Okay, let's do an example. Look at your periodic table. What is carbon's atomic weight? Well, it's 12.011, of course. So this means that if you had 12.011 grams of carbon in your hand, you would actually be holding 6.022 times 10 to the 23rd carbon atoms in your hand. Let's do another. The atomic weight of magnesium is 24.305. This means that if you had 24.305 grams of magnesium in your hand, you'd be holding 6.022 times 10 to the 23rd magnesium atoms in your hand. Ooh, okay, let's do one more. Let's take a look at xenon. Its atomic weight is 131.29. So if you had 131.29 grams of xenon in your hand, you would have, yes, you guessed it, 6.022 times 10 to the 23rd xenon atoms sitting in your hand. So that takes us to some problems. What is the mass in grams of a mole of carbon-12? You're welcome to pause this and think about it. I'm going to tell you the answer in a moment. Okay, are you ready? If we're talking about carbon-12 specifically, we're talking about only atoms that weigh exactly 12. Not carbon-13s, not carbon-14s, or not a mixture of all of the above. It's just carbon-12s, which means that if you had 6.022 times 10 to the 23rd, that is 1 mole of carbon-12s, it would weigh exactly 12 grams. Here's the next one. How many carbon atoms are present in a mole of carbon-12? Okay, that's kind of ridiculous, but by definition, 1 mole of atoms, in this case carbon-12 atoms, contains 6.022 times 10 to the 23rd atoms of that atom. So that's the answer. And then this last one, calculate the number of nitrogen atoms in 0.41 moles of NH3 or ammonia. Now I'm not going to do this one for you, but I invite you to attempt it on your own, and then if you like, you can click this link to a separate video, which I'll show you how to do it on the .cam or board. Alright, let's go on to our tricky problems. 1 mole of blank contains the largest number of atoms. Okay, once again, I'm not doing this for you, but I invite you to look at it, and then if you need to, click the link here to a separate video, which I'll show you how to do it on the board. And this one, a 30.5 gram sample of glucose contains how many atoms of carbon? Once again, I'm not going to do it, but I'll provide a link here to a separate video in which I do problems similar to this, or maybe even this exact one, I honestly can't remember, that you're welcome to check out and then attempt this on your own. That takes us to the end of this video presentation. Please stay tuned to the next one, in which I'll begin by teaching you about net ionic equations. Until next time, students, have an enjoyable rest of your day.